Hello, I promise I have no equations. So the challenge, what are we trying to do? There's a lot of data, big data, we're in the era of big data. Challenges, can we get the true signal values from the noise, track evolution, discern outliers, and ultimately obtain knowledge. There is an emerging approach, particularly in signal processing and some parts of machine learning, to connect similar data streams through network structures. So you say the edges in a network represent the similarities and influence between the data streams, and the nodes are essentially the data streams. And so what you do is you use a network structure together with signal processing and tracking and machine learning to make sense of the data. There are lots of applications. For example, online social networks. How do you discern the formation of opinion clusters among groups of individuals? This is a particular interest for understanding, how ideas form and evolve in societies. Cybersecurity, how do you estimate the network state and detect a cluster of compromised nodes? And in general, anything where you have multiple time series, so you have geophysical sensor data, the stock market, you can all start putting network structures together with the time series to make sense of the data. A lot of these applications, and our focus has been on non-stationary statistics. So you have evolving situations where the statistics are not stationary, which means that things like deep learning may be problematic here. But you have fads, malicious users, seasonal effects, things that are constantly changing. The network is time varying, so friendships could change, certain nodes gain influence, etc. Sensors go offline, some new sensors come in. And so what we do is we look at an analytical problem that captures all this, and so our work is more theoretical. These problems are basically modeled as extracting information from noisy, non-stationary signals and data emanating from time-varying networks. So we will focus on some fundamental work on this topic. What do? We use adaptation and learning to handle the evolving nature of the signals, data networks. We focus on scalable solutions. The idea is that if you have millions of nodes, you should be able to get algorithms that can handle that case. We've been using statistical signal processing and machine learning to do things like dimensionality reduction, convert high-dimensional data into low-dimensional data, distributed solutions, so you don't have to have centralized data in one spot. You can have it on parallel clusters or other types of message passing solutions. Data reduction, I don't want to look at all the nodes in the network, I want to look at some of them. So just to give you some pictures of what we've done, and the grad student who's done this work is in the audience. You can ask her, Maysar Lin. She looked at a time-varying network, and what she did is came up with a distributed adaptive tracking of signals in time-varying networks. So the network is changing, the links attributes can be changing, or new links can be forming, and edges can be dropping off. For this particular case, and then the signals themselves have non-stationary statistics. So they were following a random walk model, and she came up with adaptive, learning algorithms. And the dotted lines show the fundamental theoretical performance limits of the algorithm. So she's showing that we have an analytical characterization of performance of the algorithm. That's important for a lot of learning tasks, because right now, people are caught up with deep learning, but we often don't know why does it learn, why did it do what it did. Here we are focusing on, can we characterize using analytical performance analysis what the performance limit of the system is going to be. And so the dotted lines predict the performance of the mean squared error over time. And we have this also for time-varying networks as well. I'm not going to show you the picture. Now, the additional question, suppose I want to estimate the signal that is evolving over time in a time-varying network, but suppose there are outliers also, additive outliers. Someone is injecting malicious data. So suppose I have something like this. In addition to this, within the same estimation problem, we came up with a method for estimating the outliers. So each node is trying to estimate its own outliers. And so you can see for two of those black cases, the black dots are the outliers. You can see that the red line is our estimate of what the true outlier is. And so we have some analytical performance characterizations of this work, and we're also now working on the detection capability. How do you actually form a detection based on this? The last thing is data reduction. Okay, go back to this. Suppose I have 1 million nodes. I don't want to work on 1 million nodes. I want to work only on a few nodes, a fraction. So how do you do that? Well, this is a big problem right now in signal processing machine learning. It's called sensor subset selection, sensor selection. I only want to use a few sensors to figure out what's happening in the whole thing. And this has applications of the Internet of Things, because you have lots of devices are going to get sensors, and they're going to be reporting the performance. You want to get use only a snapshot. You know, we got a snapshot from a few of them. So we came up with an algorithm that you can use only if, you know, small percentage of nodes, and it actually performs better than comparable algorithms developed by other people who are using different programs, different methods in signal processing. But what's actually I'm not showing is the complexity reduction. Our algorithm is actually O of n cubed versus O of n to the fourth, which were the other ones. So it's, in terms of complexity, it's a much faster algorithm. And so anyway, that's all. Our work provides a framework for making sense of data from networks using signal processing, machine learning, and network science. That's all.